20 degree and at a pressure of 1 bar is flowing over a flat plate at a velocity of 3 meters per second. So we are having a flat plate, and over it air is moving, air of 20 degree and 1 bar is flowing with a velocity 3 meters per second. And here the plate is 280 mm wide. So actually only one dimension is given. So we will take this length and width of the plate. This is the width. Length and width will be taken as 280 mm, that is 0.28 meter. And the plate is at 56 degrees Celsius. That is, the entire plate is at 56 degrees Celsius. In some cases they will say the plate will be 56 after a particular distance, but here it is not given like that. The entire plate is 56 degrees Celsius. Calculate the following quantities. So some quantities are, we are asked to find some quantities. First thing that we should do is, here we are given air is at 20 degree and plate is at 56 degree. We should take the average. So 20 plus 56 by 2, that is 38. So after that, on page number 34, here property values of gases at 1 atmospheric pressure, that is 1 bar pressure, is given. So here for temperature 40 degree we are given specific things. So for each temperature we are able to get density, absolute viscosity, kinematic viscosity, and all those things from this one. So here anyway in our question it is given at 38 degree, rho is equal to K is equal to Cp is equal to this one, and Prandtl number are given. So in some cases they may not be giving this value, so we should take that from page number 34. Then so here velocity is given. The first thing that should we do is we should find the Reynolds number. So Reynolds number is ux by nu. That is rho Vd by mu can be in another times can be written as ux by nu. Anyway, we will be using this one, ux by nu. So u is the velocity 3, x is the length of the plate, and that is 0.28. It is given in the question, 0.28 divided by nu. Nu is the kinematic viscosity, and that is either we will obtain it from the table or it will be given in the question. So here at the average temperature 38 degree, the properties are given, or we will find the average temperature and we will find the corresponding values from the table. So for 38 degree we will get all those values. So nu is given, so we will substitute that and we will find the Reynolds number. So Reynolds number is 5 into 10 raised to 4. So a flow will be turbulent after, or a flow will be laminar up to this particular Reynolds number, 5 into 10 raised to 5. Anyway, our Reynolds number is 5 into 10 raised to 4. That means the flow is laminar. So the thing is that at page number 113, here external flow, and it is given flat plate. So in our case is a flat plate. So this is flat plate case, and for laminar flow everything is given. So after that, here comes, if the flow were the Reynolds number were between 5 into 10 raised and 10 raised to 1, then that case is also given. So in our case it is a laminar flow, so we will be referring this particular page. Now the first thing should be known is boundary layer thickness. Boundary layer thickness, it is given. The first thing is boundary layer thickness, rho hx. This is boundary layer thickness, and here 5x into Reynolds number raised to 0.5. So 5 into x is the length here, or it is given at 0.28 into Reynolds number raised to 0.1, that is 5 into 10 raised to 4 raised to 0.5. So here if we are substituting that, we will be getting boundary layer thickness. So this is 5 into 0.28 into 5 into 10 raised to 4 raised to. So we will get the thickness. This is point. So we will get the thickness. So the second question is local friction coefficient. For finding the local friction coefficient, look, this is CFX is the local friction coefficient. So how we will get is, if at all we do not know what is this rho hx, here it is given. Rho hx is boundary layer thickness, and here CFX is the local friction coefficient. So local friction, so for getting local friction coefficient, the formula is 0.664 into Reynolds number raised to 0.5. Reynolds number we know, 5 into 10 raised to 4. Substitute that, we will get the local friction coefficient. The third question is average friction coefficient. Again CFL. Here it is given CFL is average friction coefficient. So we should substitute that here. Reynolds number we know. We will get the average friction coefficient. Then shearing stress due to friction. So here, if we are looking here, CFX is given, local friction coefficient is defined by, that is CFX is equal to tau Wx by rho u square by 2. So from this, that is something like this one. CFX is equal to tau Wx or rho u square by 2. So we will take this particular term here. So CFX into rho u square by 2 is equal to TWX. So TWX is the thing, that is the shearing stress is the thing that is asked in the question. So CFX we have found, rho we know, u we know. U is u infinity or u, that is 3 we know. So we will substitute that and we will get it tau Wx. And next question is thickness of the, this is actually thermal boundary layer. So again, this one rho Tx, this is the thickness of boundary layer, this is the thickness of thermal boundary layer. If we have a doubt, we should go for this rho Tx, thermal boundary layer thickness. So rho Hx into Prandtl raised to 0.3. This Prandtl number we will get from the table. For that particular temperature we will get Prandtl number. So rho Hx already we have found. So rho Hx into Prandtl number we will get the thermal boundary layer thickness. Then next question is local convective heat transfer coefficient. For that NUX is Nusselt number, that is Hx by K. So Hx by K is equal to 0.332 into Re raised to x raised to 0.5 into Prandtl raised to 0.33. We know that. So that is Hx by K, that is equal to NUX into. So Reynolds number we know, Prandtl's number we know, Hx by K. X is the length of the plate, that is 0.28. K conductivity, we either we get from the table or it will be given in the question. So we know. From that we can find H, that is the local convective heat transfer. So average convective heat transfer coefficient means the thing that we should do is we should multiply this local convective heat transfer coefficient with 2. We will get an average convective heat transfer. Or we will multiply this formula, NUX is equal to 2 into this formula. Then we will get the average, or get the local heat transfer coefficient, multiply it with 2, we will get average heat transfer coefficient. Then the next question is rate of heat transfer by convection. So we have already stated that Q, if we are having the overall heat transfer coefficient, it is, we know that is equal to Q is equal to U A theta m. So this is for, if it is overall heat transfer, this theta m is logarithmic mean temperature difference. But if this were heat transfer coefficient, not overall, but heat transfer coefficient H, then H into A into, here theta m is logarithmic mean temperature difference. But if it is H, we do not want that logarithmic, we want just temperature difference, that is delta T. Delta T means temperature difference, and here the temperature difference is the temperature difference between the air and the flat plate, that is 56 minus 20. So H is the one that we should find. So Q is equal to HA Ts minus T infinity. No, H we know. H is the this average heat transfer coefficient that we know. Area is here 0.28 is the only dimension given. So we will take length and breadth is equal to 0.28. So length into breadth, that is 0.28 into 0.28. We will get the area 56 minus 20. So we will get the this particular thing, rate of heat transfer by convection. Then total drag force. We have already found the shear stress. Stress in the area is the force. So TW into area is 0.28 into 0.28. You will get the total drag force. Then the total mass flow rate, that is given by a formula. It is actually this one, 5 by 8 into rho u into delta 2 minus delta 1. So this particular one. And here this delta 2 means that is the boundary layer thickness at the end here, that we have already found. That is the first thing that you want, boundary layer thickness. Delta 1 is 0. So we will get it marks.